So next and last, we hear from the Grandad of Computation, Robin Cockett from the University of California.
Okay, well, thank you for letting me speak at this meeting. Okay, I'm going to do the background. I'm going to do a reminder on restriction categories, and then I'm going to talk about Turing categories. Oh, what I shouldn't mention, this is work which, as you know, we've been putting out a Pieter Hofstra volume. So I was sort of looking back through the work that I was doing with Pieter Hofstra. And I have this work which is unfinished with Pieter, which he did with Jérôme Fortier. So I was sort of looking, maybe we should push this out. Gordon Luang is an undergraduate student. So everything I'm talking about probably can be understood pretty well by an undergraduate. So it's an appropriate for a late Sunday afternoon talk. Okay. So I'm going to cover these things, hopefully. And I'm going to go into handwritten slides. So let me remind you that Schonfinkel in 1920 introduced combinatory logic. We would call it combinatory algebra. So what one of these things is a set with a binary operation. Let me put my pointer there, binary operation, and just two elements, S and K, which satisfy just two identities. So K, X, Y. So I'm writing the application in the standard way, where the space stands for application, and then you write associate. So this has the brackets around KX, and then you apply that to Y, and that equals X, and then SXYZ equals XZYZ. And the amazing thing is that a combinatory algebra can express all computations. It uses, in order to actually do the computation, you use a rewriting system. And the rewriting system is just the obvious one. It just orients the two identities you have. And okay, so it turns out to be a little bit tricky to prove with CAR that this is actually a confluent rewriting system. And it's important to realize that all the problems arise because it does not terminate. So you have to handle the non-termination. So let me just remind you what confluence means. So you see, if you have some combinatory term, P, sitting there, and you randomly rewrite in two different directions to Q1 and Q2, and I call that a divergence, then confluence says that there is a way of converging these to a common term. So every divergence has a convergence. And in fact, in combinatory logic, this is actually a push out in the two-cell world. Okay, so what makes it able to do all computations is that it's functionally complete. And that means you can simulate lambda abstraction in this little algebra. So you can construct a term, lambda star x dot t, such that when you apply it to S, implements substitution. And so it gives you t with S substituting for x. And right, the way you construct this term is, I mean, literally, you can write down the equation. So, for example, lambda star x dot y, where x and y aren't the same variable, is just ky. Lambda star xx, well, that's skk. Skk always gives you the identity map. And then lambda star of an application of two terms is done by writing S lambda star of T1, then lambda star of T2. And then you can prove by a structural induction that equation happens. Well, in 1975, Solomon Feferman introduced partial combinatory algebra. And this was quite a sort of important transition, because if you think of the models of standard Turing computations, they're partial. I mean, not every computation terminates, and so you get a partial computation. And you might ask, why was there such a big gap? I mean, there was over 50 years between the two steps. And one possible reason for that was that the tools for partiality were a bit rudimentary. So from these PCAs, partial combinatory algebras, on the one hand, realizability hypotheses grew, but also, as we're going to discover, Turing categories also sort of grew from that idea. Okay, and Turing categories were done by Pieter Hofstra and me in 2008, and we sort of claimed grandiosely, maybe, that it covers all examples of computability. But we sort of reframed it all in terms of restriction categories, and I just want to go through that quickly. So what is a restriction category? Well, it's a category with a restriction. So a restriction is a structure which takes an arrow, A to B, and returns an arrow, which is an endomorphism on the domain of that thing. And that F bar represents the partial identity for which the partial map A to B is defined. And it satisfies just 4 identities. So I'm writing this in diagrammatic order. So F bar first, then followed by F is F. If you have 2 restrictions on the same object, then they must commute. You can force the restriction underneath the restriction of another map, as so. And R4 is a more powerful axiom. And what it says is if you do a restriction after a map F, you can move the restriction in front by composing the map and then taking the restriction of that, and then following it by F. So here's a little example of reasoning with restriction categories. So you can prove that FG bar equals FG bar barred, right? And here's the little proof, just to get you sort of into restriction categories. So the first thing you do is you push the restriction forward using R4 underneath the restriction. Then you pull it out using R3. And then you flip the order. And then you push F bar back in. But now you have F bar F, which of course is F, and that gives you FG. So in a restriction category, a function is total in case the restriction is the identity map. So thinking about partial maps, you're thinking about the partial identity. And of course, if it's the whole identity, then it's a total map. And the total maps form a subcategory, and there's a little proof which uses this identity that these things compose successfully. We'll also, I should mention that there's a partial order on the map. So really this is a sort of enrichment in partially ordered sets. So restriction categories are sort of 1.5 categories. So the partial order is defined by saying that F is less than or equal to G if F bar G actually equals F. And we're going to use the partial order in a second. So, so one of the things you need in order to talk about computability is products. But in partial map categories, products don't behave quite like normal products. They still have the same diagram, but the uniqueness of this arrow is only up to a laxity. It's a lax situation. And in fact, this thing actually, if you take the restriction, is the joint restriction of the two maps that you're mapping in. So if you just think about what happens if this map is partial and this map is partial, well, if you're going to get a map to A cross B, you can only be defined where both of them are defined. And that's the reason for this. And there's also the notion of a restriction final object. So as before, a final object has a map, which I'm calling bang X, which is total to the final object. But it isn't unique, but any other map, whoops, what did I do? Yes, any other map here to 1 can be written as the restriction of F followed by this bang. So it's just a restriction of this, this final map. Okay, so some examples, of course, sets and partial maps. There's a Cartesian restriction category. And F bar is defined just as you expect it to be defined. It's X if Fx is defined and undefined if Fx is undefined. In general, any partial map category is a restriction category where you take the system of monics here and X, and then the objects are the objects of X. The maps are little spans, and then composition is by pullback. Now, when you deal with the spans, you have to deal with spans up to equivalence, where you get an isomorphism between the apex of the two spans. And the beauty is that restriction categories remove from you the necessity of talking about pullbacks at all. And you can deal with things totally algebraically. And in fact, every restriction category embeds fully and faithfully into a partial map category. So in some sense, the partial map categories are completely captured by the notion of restriction category. Okay, so Turing categories. So a Turing category is, so these were introduced by, oh God, I'm blanking. It'll come back to me, and I'll tell you. So it's a Cartesian restriction category. Well, it was introduced by Pieter Hofstra and I, but there was a precedent to this. So it's a Cartesian restriction category with a Turing object, and that means for every A and B, there is a map, which is called application, from A cross, try not to, A cross T to B. And for every map, F, from A cross X to B, there is a total map, which tells you how to express this in terms of the application. So here's the total map here, and then you compose, followed by the application of that thing, and you'll get back F. And clearly, application is going to be a partial map because these Fs are partial map. And it's important to realize that the F tilde is not unique, and it's very not unique in most examples. Okay, and you can simplify the notion of a Turing category because every object in a Turing category is actually a retract of the Turing object. So that means every object can be seen as a retract followed by a section of the Turing object. And you can see this by just using the bullet to the final object and x. And here using the projection, and then you get your desired S. So this is the S and this is the R. So a Turing object is universal in the sense that every other object in the category is a retraction of it. And then you can simplify the definition. So down to demanding that T is universal. And there's a Turing map just for the, so this would be written bullet TT. And if you have that, you can then generate all the other Turing maps. So in the end, it's quite a simple definition. Right. And furthermore, you can quickly notice that there are total elements, S and K, which satisfy the identities of a PCA. So here, for instance, is how I define K. What I do is I take the map 1 cross T, and I project to get this middle T out here. And that, of course, is giving you the action that you want of K. And then this K is now representing that map. And this map is just the composition of the applications where you hold, where you associate the applications like that. And then to do S, well, you do the same. It's a little bit more complicated because you have to do the right projections. And of course, there's a duplication that's going on. So pi 2 here is duplicated across here. And then, and that gives you your S. And of course, it's got to be total because by Fiat, you've got to ask that the map which gives you the index for this thing is total. So that means, in fact, that you get what's a partial combinatory algebra sitting inside any Turing category. And so what I'm calling the granddad of all computation is the generic PCA in a restriction category. And I'm going to come back and talk more about what a PCA is in a moment. But the idea is that you have a generic PCA sitting in a restriction category, and any Turing category with a chosen Turing structure, of course, has a PCA on that structure, and that induces a map here. Now, so the hope is that this thing is the initial Turing category. And that's the sense in which I'm using granddad. But actually, there is something we've got to show because it's not clear that this thing, RT, actually is a Turing category. Because remember, we've got to have a Turing object with the unique index, not unique indexes, with indexes. So, and the question is, well, how do you get indexes out of there? So what I'm going to do before we do that, so I'm going to explain how you get all that out, but I'm going to talk a little bit about the internal language of Turing categories. And actually, this dates right back to Moji's PhD thesis. And he was interested in the partial lambda calculus and trying to get out a confluent system for that. And it was significant that he failed. And actually, I asked him what he thought about that, and he said, "Oh, God, that was a mess." So I think he just gave up at that stage. But essentially, I just want to explain this internal language a little bit. You've got variables for types, and you have your operations, which can be partial. And then you express the restriction by having a map T and a map S, and then forming the map T with restriction S. And oh dear me, and I've got the wrong, this should be an A. Sorry. Oops, and then yeah. So this ends in A. So it ends where A ends. And the point is that this term behaves as T does, but it's only defined when S is defined. So what you add is the partiality of S by this slash operation. And then you can notice that there are a bunch of identities which are true of this restriction. So if you restrict by S1 and then you restrict by S2, well, it's going to be the same as restricting by S2, then S1. And if you take T and you restrict by S1 restricted to S2, well, that's the same as this. So we tend to write the restriction with commas after it, just to say that the order doesn't matter, and in fact, the stacking doesn't matter either. And if you restrict by a variable, then of course it has no effect. But there is a rather important rule that if you restrict T by T, well, that's T. And this is restriction elimination. And it was this rule that causes all the problems. And okay, so I'm going to now express a partial combinatory algebra in these terms. So you have a partial map, which is application from T cross T to T. You have a couple of total elements, and then you have a bunch of equations. Now, the S equation is completely unchanged. The K equation is changed because you get P out, but you can't lose the partiality of Q. So what you do get is P restricted to Q. And then if you have some term and you restrict it to S applied to P and Q, then in fact, essentially what the S applied to less than the number of arguments that it actually wants to be applied to, because you should be applying it to 3. So if it's applied to 2 arguments, then it's essentially total as a map. But of course, you can't lose, again, you can't lose the partiality of P and Q. So you get V restricted to P and Q. And then similarly, if you shorten it even more and just have one argument of S, then you get the restriction to P. And of course, S by itself is total. So you just get V. And similarly with K, so KP actually turns into K restricted to P, right? And similarly, K, of course, can be eliminated. Okay, so this gives a little algebraic description of a partial combinatory algebra. There are some other identities, and here I'm just mentioning, and this just follows from the fact that it's a Cartesian restriction category. That when you have the application and you restrict one of the arguments to Q, well, it's the same as restricting both the arguments to Q. So you can pull restrictions out. Okay, so now what we have to show is that it's actually this actually generates a Turing category, and to do that, what we're going to do is we're just going to do this lambda star translation. So again, the lambda star translation is virtually unchanged. So you have lambda star XX is SKK, and that's just the identity in combinator speak. And then lambda star XY, XY is KY. Lambda star X T1, T2 is, it's unchanged, right? It's S of lambda star T1, lambda star T2. And so this is the new bit. So lambda star of T1 restricted to T2 is this funny thing. It's SS, KK, lambda star of T1, lambda star of T2. And then what you can do, well, is you can prove a lemma. The first important thing is that when you do a lambda star x of t, this is actually a total map. So you remember in a Turing category, you had to have that index being total. Well, this is what guarantees that, because this is going to be the index. And then the other thing you want is that substitution lemma. So, and you can prove this by structural induction. It's very straightforward. And then you get T1 is T2. Oh, no, sorry. T2 substituting x, but you have to do restricting to T2 because there may be no x in T1. And you can't lose the restriction of T2 in that process. But anyway, that little lemma actually proves that you get a Turing category out from the Cartesian restriction category with a generic PCA in it. So, and that's the statement they'll get there. Okay, so that's good, because now, in order to understand the Grandad of Computation, all we have to do is look at a restriction category with a generic PCA sitting inside it. And so what we wanted to do was then to look at the rewriting theory for this. And this caused us a lot of agony. And part of the reason is because when you're rewriting something with a duplication, the usual way to do it, I mean, you think of the distributive law in algebra, you do the rewriting in the direction of duplication. But in fact, it turns out in this case, you want to do it in the other way. And this causes all sorts of problems. Okay, so I'm going to sketch how this rewriting theory works. And so what you have is a bunch of two-way rules. And these rules just allow you to move the restrictions around. And in fact, you can flatten out all the restrictions so they all sit at the top level and they just restrict the main term. And you're going to leave the elimination of the restriction in. And then you're going to just have the usual rewrite rules for S and K. But then you have to have a bunch of other little rules which tell you about what you can do when you've got you're restricting by one of these combinators with the wrong number of arguments. And so there are these rules which do that. And okay, and the objective is to prove that this actually produces a confluent system modulo, well, I shouldn't say, subject to these equivalences. And the equivalences just allow you to move the restriction around in the term. Okay, so we're still really working on this, but at this stage, I'm pretty certain it works. But until it's written up and beautifully in LaTeX, there's still a little uncertainty. Okay, so what's the plan? So you're going to use the equalities to get the term into the form T with restriction of S, where S is a bunch of terms, and all the terms T, T1 through Tn have no internal restrictions in them. So what you've done is you moved all the restrictions to the one sort of restriction at the top level. Okay, so the next step, which I'm going to say more about, is to use a marking argument. So this is a very standard argument for proving the confluence of the lambda calculus or the combinatory algebra. So you actually mark terms and the rewrites you want to do. And then there's a process for removing the markings. So what you do is you do a rewriting by value, working up from the leaves, but you leave the restrictions in that process, and then finally what you do is you do all the restriction eliminations, and that actually gets rid of all the markings. But we'll see it's a little bit more involved than what I just said. But we're talking about the plan. The next thing is to use the strip lemma. So the strip lemma essentially says that if you can do one rewrite against a number of rewrites, where each one of these can have multiple rewrites down the bottom, and there could be multiple rewrites here too, then you can prove confluence. And what that involves, the way you do it with markings, is you mark one rewrite down here, and then you have one rewrite here, and then you get a marked rewrite. Oh no, a marked rewriting going down. Okay, so and then there's a fourth step, because when you rewrite the top term, or indeed any term in this system, of course, what happens is you've got an elimination of t happening on this s, and then you've gone and rewritten s. And that means you can no longer eliminate t on s. But what you can do, obviously, is if actually t is provably equal to s, you can still do the elimination. So what you do is you put a proof on this link. And the proof actually is a little divergence with many steps on both sides. And right, so this is restriction elimination with a proof. And then, so the final step in the proof is to get rid of the proofs on the elimination step. And this is a little bit subtle, so that you don't get into trouble each time round that you start eliminating these things. Okay, so let's just talk a little bit about what I mean by marked reductions. In order to indicate what things you want to rewrite, the simplest way is just to mark the S's and the K's. And I've marked them in red. Now I got a rewrite rule here, and I got ... And that doesn't mean that it rewrites to that. It means that it rewrites to the usual thing with S removed. And so you just do the S rewriting across here and the K rewriting here. So this would rewrite to P restricted to Q, for example. And then you also have these other rewrites that you had to worry about. Now, because you've moved all the restrictions up to the top level, these don't cause a lot of bother, shall we say. Right, so we got all those things. And also, we have the elimination steps, right? And so actually what we do is we just make this a red pointer to the place where you want to eliminate it. And you've got to allow a proof on here. So that defines the notion of a marking. And then the question is, well, how do you remove the markings? And what you do is you work from the leaves up. When you hit one of these marked terms, actually you just forget about the eliminations to start with. You just eliminate the S's that you've marked, and you work up from the root. Now you've actually got a whole bunch of trees, because you've got all the restrictions and you've got the main tree sitting there, and you do this on all of them. And of course, what happens as you do that is the places where you wanted to eliminate get rewritten, and so you have to introduce proofs onto your elimination pointers. And in fact, there's another special case, which I should just briefly mention, is you see when you have a pointer halfway into an S regex, then of course the S disappears, so you get this pattern, and you have to separate these two things onto two different things. Now, this could be embarrassing because you've actually got proofs here, but the point is you have no reduction steps which happen at the top level. All the reductions have to happen in P and Q, and that means you can actually move down. You can split the proofs. Oops, right. Okay. And then, given that, you can prove you do have this property that if you have red rewrites here and you have a single ordinary rewrite, then you can actually complete the square. And this is part of the strip lemma that you're going to sort of go like that, by eliminating all the red material. However, the restriction elimination still has proofs sitting on those pointers. So the final step is to remove the proofs, and that is done by rewriting this time from the top down, and then all the terms from the top down, and the effect of that is to make that little divergence, which is a proof, to have the right-hand arm an equality. And then what you do, you work up from the bottom of the tree of restrictions, and you remove all the you can then remove all the restrictions by rewriting those terms and actually doing an elimination T/T on those things. Okay, but it all seems to work to my surprise. And let me just, I'm finishing off now. How you rewrite the partial lambda calculus has been an open problem since Murgy's thesis, which is about 30 years ago. And although this hasn't addressed that problem, we think these techniques work for the partial lambda calculus. And I mean, the whole, the reason I think that Murgy got into trouble and it made such a mess was because he was trying to rewrite in the opposite way. And by doing it in this way, we think you can keep track of things much more tightly. Okay, that's the end. Thank you very much.
Okay, let's thank Robin for a great talk. And
can I?
Any questions? Before we thank the organizers, let's see if there are any questions.
Oh.
Or comments.
Comments. Can I also put that one up too?
Yes.
I have
a question.
Yeah.
Yes, Bill.
An answer.
Okay. Well, Robin, that was very nice, and I have a whole bunch of comments to send you privately by email. But just publicly, when you rewrite backwards, like the eta rule, that's often called eta expansion.
Ah, right.
And there's a whole theory of typed eta expansion due to George Chubridge.
Right. And
student of Mackay. And the point is that you can't keep going forever. And eventually this process must stop. But it's a very, very tricky analysis. And I think it got mostly abandoned in the literature by Kurian and others to use a different kind of logical relations argument. But Chubridge's expansionary rewrites are really quite interesting, and they apply sort of in your case because you're typed.
Oh, I'm untyped, actually.
Well, but you set up a typed system there.
Well, it's unityped. Okay.
Yeah, unityped, if you like. Yeah.
Yeah.
So anyway, I like that a lot. That was very interesting of your stuff there. So that was very nice. I have lots more questions, but I won't waste people's time.
So can I ask a question? So Shubrick's stuff would use the rewriting in the opposite direction, T to T/T, would it, as an expansion?
Yeah, it was. If you have the eta rule, which is lambda x f applied to x is f. Instead of rewriting it left to right, you expand it the other way. F goes into lambda x fx, and then it looks like you keep doing that, and you keep doing that and doing that and doing that. It looks like it should go on forever, but there are various type constraints that the kind of Cartesian closedness imposes, and that causes it to actually die out after a while.
Oh, right.
And yeah, it was very important. It was used in proving Friedman's theorem and other things for Cartesian closed categories. Yeah.
Okay, thank you.
Any other comments or questions? If not, let's thank Robin again.